Here in this video, we want to derive a relation between molar specific heats of gases at constant pressure and constant volume, right? So let us define them once so that we can derive the relation quite easily. Yes, what we can say is molar specific heat of a gas at constant volume is defined as amount of heat required to raise 1 mole of the gas by 1 degree centigrade at constant volume. As we keep the volume constant, change in the volume is equal to 0. But we know as per the first law of thermodynamics, dq equal to du plus dw. The dw can be written like pdv. This dv is change in volume, that is equal to 0. So du plus pdv is 0, so that is equal to du. So I can rewrite the definition of specific heat of a gas at constant volume as 1 by n. In the place of dq, I can write du by dt. From here, I can write du equal to n cv dt. This is one expression. We'll use this later basing on the definition of cv. Now I can go ahead and talk about definition of cp. Molar specific heat of a gas at constant pressure is defined as amount of heat required to rise unit mole of the gas by 1 degree centigrade at constant pressure. As pressure is kept constant, change in the volume is not equal to 0. That implies the format of dq is not going to change in any way. So dq can be written like n into cp into dt. So you got one more relation. dq is how much? You know du also how much? Now let us write them in first law of thermodynamics. What we can write? As per first law of thermodynamics, the total heat energy supplied to a system dq is sum of change in internal energy and the external work done by it. But in the place of dq, I can substitute this value that is derived from Cp. In the place of du, I can substitute this value that is derived basing on the definition of Cv. Let's do that. So in the place of dq, n Cp dt equal to, in the place of Cu, n Cv dt plus in the place of dw, as per the definition of the work done, I can write pdv. So I can get this term to this left hand side, n Cp dt minus n Cv dt equal to pdv. So n of Cp minus Cv dt equal to pdv. But we know, as per an ideal gas equation, as we are writing a relation for an ideal gas, for an ideal gas, equation is PV equal to nRT. So if I differentiate that at constant pressure, PdV can be written like n and r are constants, nr dt. So in the place of this PdV, I can write this value nr dt. That implies what's going to be my equation? This equation, n of Cp minus Cv of dt is, in the place of PdV, I can write as we have derived nr dt. N and n can cancel, dt and dt also can cancel. So what is remaining is Cp minus Cv equal to R. Capital R is called as universal gas constant. That's how we can derive a relation between Cp and Cv, that Cp minus Cv equal to R. Anyway, we can extend this discussion a little further and derive few more things. What are that we can derive? Let us see. We know as ratio of specific heats of gas Cp by Cv is defined as gamma. In the place of Cp, I can write gamma into Cv. So as we have derived an equation Cp minus Cv equal to R, in the place of Cv, I can write Cp, I can write gamma into Cv minus Cv equal to R. If I have taken Cv common here, gamma minus 1 equal to R. So Cv equal to R by gamma minus 1. This is one way of writing Cv. And I can also further write C from this relation. Basing on the definition of Cp by Cv is gamma, I can write Cp equal to gamma Cv. So from there I can write as Cp equal to gamma into Cv, Cp equal to gamma into Cv means we have already derived an equation R by gamma minus 1. Thus we can express Cp's and Cv's in a different formats also as shown here, and we can derive a relation between Cp and Cv basing on the very definition of Cv. We have used only definitions and Cp. So that it's a very simple definition, simple derivation. We can further extend this in the later videos about this discussion. Right? Thank you for watching.